Move on. Okay, let's go forward. All right, centripetal force. So another common force you may encounter that we have not yet talked about is the centripetal force. Centripetal force is always present whenever you have anything spinning in a circle. So say if you took a string with a ball on it and then you just spun it in a circle, centripetal force. If you had a car moving in like a circle to make like a donut, centripetal force. If you have a planet orbiting the sun, centripetal force. Everything has anything moving in a circle has a centripetal force, right? Unlike the forces we've already talked about, like friction or tension, centripetal force is a net force. So we've actually talked about net forces before, like we mentioned in, I believe, one of the old slides. If you want to talk about this slide, the net force up and down combined was 0. F net in the y direction was 0, right? But F net wasn't an individual force. It was a combination of different forces. Well, that's what the centripetal force is. It's a combination of different forces that we just gave it a name. It's called a centripetal force, okay? So like we had here, F net was 0. It's a combination of total force. Centripetal force is a combination of different forces that we just gave a special name, okay? When you're moving in a circle. What it means is there's always a centripetal, so there's always a centripetal force and it always points in the middle of the circle. So if you think of the planet orbiting the sun, the centripetal force always points towards the sun. Doesn't matter if the earth is here, it always points this way. It points this way towards the sun. If the earth is here, it points down towards the sun. If it's here, it points left towards the sun, no matter where it is, it always points towards the middle of the circle, okay? And same thing with the centripetal acceleration. If you have a force pointing inwards, that means F equals ma, you also have an acceleration going inwards, okay? So a car going in a circle is always accelerating inward. A planet orbiting the sun always accelerating inward towards the sun, if you want to think about it that way. And it's made up of different forces that we've already talked about: tension, gravity, spring force, anything. The exact composition of forces depends. For example, with a planet orbiting the sun, most of the force is gravitational force. So most of the inward forces are due to gravitational force. If you have a ball spinning on a string, most of the force is tension from the string. It depends, right? But the key thing is centripetal force is a net force, okay? The way like I mentioned, centripetal force always points in the direction of the epicenter of the circle. Its magnitude is always equal to mass times velocity squared over r, mv squared over r. That's what centripetal force always equals to. And unlike where I said make a force diagram, with centripetal force, like I mentioned, it's a net force. You can always just find it using this formula. Sorry. The acceleration of an object also always points to the center, like I mentioned, and it's defined by this formula. Acceleration, centripetal acceleration is equal to v squared over r. If you can actually derive this from, again, classic formula, F equals ma. If the centripetal acceleration is v squared over r, in order to get centripetal force, you just multiply this by m, and voila, we have mv squared over r. Very easy. Okay, and that's how you always find centripetal acceleration, centripetal force. Velocity is instantaneous velocity, and this is where I was talking about the difference between instantaneous and average velocity. At different points in the rotation, the object will have different instantaneous velocity. So for example, if you're a planet orbiting the sun, the planet is always orbiting the sun has a velocity, if it's at the bottom and it's going in a circle like this, right? When it's right here, it has instantaneous velocity going in this direction, exactly to the right. And then it has like this. It always follows the circle. The velocity always follows the circle, whereas the acceleration always points upward, right? And if you're having a question like this, they'll give you the instantaneous velocity. They'll give you the radius of the orbit, right? The r is the radius of the orbit. And they'll give you the mass of the object, right? It's the mass of the object that's orbiting, right? And F equals the force. This question, I don't want to spend too much time on it because we were already going over, so I'm just going to skip this question. Motorcycle, and I'll go over it together. Motorcycle moves around a curve of radius r with speed v. Later, the cycler increases the speed to 4v and drives around a larger radius of 4r. By what factor does the centripetal force on the cycler change? The answer is 4. And we can see because, so we know that F equals mv squared over r. And we'll call this F1 initially, and we'll call F2 after a certain time. We'll say V1, R1, V2, and R2, right? We know that V2 is 4 times V1 and R2 is 4 times R1. So we can actually substitute it like this, 4 times R1, and this is V1, 4 times V1, right? Now, let's simplify it. Now, this cancels, this cancels. Okay. So now let's track it. So we put the 4, so the velocity is 4 times what it originally was, and the radius is 4 times what it originally was. Because the velocity is 4 times, but you square it, so it's actually 16 times. So the squared is actually 16 times more, right? Rather, where this is only 4 times more. Again, 16 and 4 cancel out, and you're left with 4 mv squared over r compared to mv squared over r. That means it's 4 times greater, right? And you can figure this out easy just because you know there's a squared at the top, no squared at the bottom. So if you increase by the same factor, the top will always increase by more just because it's squared. Does that make sense, or do you guys want me to go over it? Any questions? Anything? Okay. Last step is gravitational force. So the final non-electromagnetic force you may see in the MCAT is the gravitational force. We've already discussed the effect of gravity on us by the Earth, but any two bodies that have a mass always have a gravitational force towards each other, right? And if we're talking about direction, it's always towards the object. If I'm standing here and I have a water bottle right here, my gravitational force is always going like from mine's towards the water bottle is going towards the water bottle is going towards me, right? The gravitational forces are always towards each other, right? And we do have a gravitational force, even though you don't think of it that way. We always do. It's just extremely, extremely, extremely small, just because we're not massive. We're like very small, and we'll see why that is in a second. The gravitational force is so small in most cases. The only time it actually becomes relevant is when you have two objects with very high masses. So such as planets, moons, stars, something like that. Even like big animals like whales wouldn't have a gravitational pulse or force because they're just very, very small compared to a planet, right? We'll talk about why that is. Look, the formula for gravitational force is big G times m1 times m2 over r squared. Big G is a constant and it has a fixed value. M1 is the mass of object 1, M2 is the mass of object 2, and r squared is radius squared. Radius squared is the distance between the two objects, but it always goes from the center of mass of the two objects. So for example, the center of mass of the Earth is the center of the Earth. So it's always the distance from the center of the Earth to whatever other object it is. And that's one of the reasons why for us it's 9.8. Because when it's 9.8, it would change when you're going on a different altitude, but the center of the Earth is so far away from us that even if you were to go like 20 feet, 30 feet, 40 feet, 100 feet into the air, the difference would be like very insignificant from where we are now, how far away we are from now from the center of the Earth, right? So that's why the gravitational, the little g, acceleration due to gravity is always 9.8 for us. Technically, it always changes depending on altitude, but by such a small amount. Big G is, I mentioned, a constant, value 6.67 times 10 to the negative 11. I would recommend memorizing it, but they might give it to you on a test, so up to you. I'd still recommend memorizing it just in case they don't. The units are newtons times meters squared over kilograms squared. Again, you can figure this out. This is kilograms, so you have 2 kilograms in the numerator, means you have to have 2 kilograms in the denominator. Radius is distance, so distance squared, 2 distances in the denominator, 2 distance in the numerator. This cancels out with the radius squared, this cancels out with the 2 m's. All you're left with is newtons, which is equal to force on the left side. Units on the left equal units on the right. Again, because big G is so small, if you calculated this using my mass and this water bottle's mass, the resulting force would be like 10 to the negative 100, or 10 to the negative probably 10, 11 units, newtons, which is so small compared to like this has like a gravitational force from the Earth of probably like 10 newtons, right? Somewhere around there. 10 newtons versus 1 times 10 to the negative 10 newtons, big difference. So the only time that gravitational force really matters is when the 2 objects are massive, okay? And yeah, does anybody have any questions about this? How to calculate gravitational force, centripetal force, anything like that? Anything we've covered in this lecture so far? And so this is the end. I actually have to change this slide because this is old. Office hours are not Saturdays at 12 to 2 p.m. Sorry, this is a mistake. We will try and get the PowerPoint recording out to you. If you don't find them, please email me at this email. I'll send them to you. But thank you very much for joining us. Sorry it took so long. Yeah, it was just because we had a lot of questions. And I tried to kind of go in detail, and this was a big topic. For the next lectures, I will try and make it a lot shorter, a lot more concise. Yeah, as mentioned, all lectures will be Thursday, Friday, and Saturday at 8:30 to about 10:30. So please join us tomorrow, join us Saturday if you have. Look at the schedule on the GroupMe, join the GroupMe if you haven't already. There you'll find all the updates. The schedule is there as well, the spreadsheet, to see what topics are going to be covered.
Awesome. Thank you, Mark. And I know it was long, but the questions were really